What's up, my stat stars? Michael Princhuk here, ready to start helping you prepare for the AP Statistics exam in May. In this video, I want to walk you through some multiple choice questions that deal with inference for categorical data, focusing on chi-squared, and inference for slopes. This is Unit 8 and Unit 9 from the course exam description, and these two sections together usually make up around 4 to 10% of the exam. So to be honest, not a lot of multiple choice questions are going to come out of these two units, but there's definitely going to be some on there, and if you can get these right, then you're going to be one step closer to getting that score that you want. Now, I promise that the questions I'm going to go over right now are not the exact same ones you're going to see on the exam in May, but they have the same ideas and overall concepts. And if you review this, watch me solve these problems and understand the concepts, you're one step closer to doing really, really well on the exam. All right, let's start taking a look at them now. Before we start to take a look at some chi-square tests and inference for slope multiple choice questions for the AP exam, let's talk about what's on the formula sheet that relates out of these two units that might really come in handy. First, for chi-squared, here is what is told to you about chi-squared on the AP Statistics formula sheet. You are given the basic formula for the chi-squared statistic. It is going to be the observed values minus the expected value squared divided by the expected. You're going to do that for every single observation, and then you're going to add all those together to get your total chi-squared statistic. So that's something you're definitely going to, most kids have this memorized. It's not overly difficult, but it's nice that it's on the formula sheet in case you forget. Now, there's also a box on the very back of the formula sheet that's all about inference for slope. So here it talks about building that sampling distribution. It talks about the mean of all possible sample slopes is the true population slope beta. And then we also have the standard deviation for that sampling distribution, and that requires us to know some of the standard deviations of the population. But obviously, typically we just use standard error, and here's the formula for standard error, and that's just where we replace some of those sigmas with our s's. Those are the standard deviations from our samples. But what I have to say is this: you will honestly never, ever, ever need this formula. Really, you won't. Because if you're going to be asked about inference for slope, you're going to be given a computer output table, and in that table is the standard the standard error of the sample statistic. You don't have to do anything to it. It's actually given to you. They actually do all the math for you. And a couple of examples we're going to look at today, you're actually going to see that. All right, so here is our very first problem. In order to plan its next advertising campaign, the trendy motor vehicle company is investigating whether the type of vehicle and the color vehicle are related. Each person a random sample of size 275 selected from the company's mailing list was classified according to the type, car, or truck, and the color of vehicle he or she drove. Here is the data in our two-way table. So across the top, we see the vehicle color, and across the side, we see the vehicle type, car, or truck. Now, which of the following procedures would be most appropriate to use for investigating whether there is a relationship between vehicle type and color? Now, the first thing I noticed that these are all counts. None of these are means. None of these are proportions. These are all counts of data, which is exactly what chi-squared is for, looking at counts. I counted 35 people who bought a red car. I counted 55 people who bought a black truck. So I'm not going to use a 2-sample t-test or a 2-sample z-test or even a matched pairs test, because that's all for sample proportions or for sample means. We're not looking at that. We're looking at counts. So now I know that I want to do a chi-squared test. But is it a chi-squared goodness to fit test or a chi-squared test for independence? Well, it's going to be a chi-squared test for independence because I see a two-way table, and I'm clearly asked about looking for the relationship between two different variables, the type of vehicle and the color of the vehicle, which is exactly what a chi-squared test for independence does. Now, a chi-squared test for goodness to fit is used when there's only one categorical variable. Like if all I was looking at was the color of the vehicle, didn't care if it was a car or truck, that would therefore be a chi-squared goodness to fit test. An independence test is going to be when there's two categorical variables in a two-way table. Now, they didn't give you an option to select for a test for homogeneity, but another chi-squared test is for homogeneity, but that would be where we also have a two-way table, but it came from multiple samples, and we're looking at what we see across those multiple samples. But based on this problem, we only saw one sample of 275 people. We just asked them two different questions. So I know we didn't even have the option for homogeneity tests here, but that could be an option when it comes to chi-squared. But this is definitely a chi-squared test for independence. All right, here is a very classic question when it comes to inference for slope. So a part of a class project at a large university, Amber selected a random sample of 12 students in her major field of study. All students in the sample were asked to report their number of hours spent studying for the final exam and their score on the final exam. A regression analysis of the data is given in this computer output. Amber wants to compute a 95% confidence interval for the slope. Okay, assuming all conditions are met, which of the following is the margin of error? Now, a confidence interval for slope starts off with your sample slope. Now, if you're ever confused about how to find that in one of these tables, all you got to do is look at this very first column here, and they go in order A and then B, and B is your slope. So the slope is 2.697. So that would tell me that in this data, for every 1 additional hour spent studying, the score on our final exam predicted to increase by 2.697 points. All right, so when I'm going to find this margin or this confidence interval, the first thing I'm going to do is I'm going to start off with that 2.697. Then I'm going to go up and I'm going to go down by the margin of error, which is exactly what they want me to find. Now, the margin of error is a combination of two things, my critical T-star and my standard error. Now, if we look at that, all of them have the same critical T-star. So that's not going to determine what's the correct answer, but I do think it's worth me showing where that came from. So they want me to be 95% confident. So when I go to invert T here to find my T-star, I want to put 0.025 at that bottom area. Again, 95% in the middle, 5% gets left out, 2.5 at the bottom, 2.5 at the top because of symmetry. So when you use invert T, the area it's asking for is the area at the bottom, which in a 95% interval would be 2.5%. Now, she said that she looked at 12 friends, which means she has 10 degrees of freedom because we have sample size -2 when it comes to the degree of freedom for slope. All right, and that's where we get the 2.228 from. Now, that's the same for all of them. Now, what about the standard error? Well, again, it's literally right in your table. You do not have to do any work to find it. It's literally right next to the slope, right here, 7.45. I don't have to do anything with that number. I don't have to use any fancy formula. Again, go back to that formula sheet that I already showed you. There is a formula to get that standard error, but you don't have to worry about it, which makes choice A really, really simple. Here is my T-star, 2.228, and my standard error for that slope, 0.745. So simple. All right, in this question, it says a sports physician conducted a study to investigate whether there is an association between running experience and the occurrence of a certain sport injury for marathon runners training for a marathon. Data was collected on a random sample of 51 marathon runners. Each runner from the sample was categorized by running experience, low, medium, and high, and whether or not they experienced a sports injury while training. So the conditions for inference were met, and the chi-square test statistic was 8.12. Which of the following describes the p-value? Okay, so I have to find the p-value based on a chi-square test statistic of 8.12. So the p-value is the probability that any other chi-square test statistics would come back more extreme than the one I got. So to get that, I'm going to go to my handy-dandy calculator. Second, VARS is going to get me to chi-squared CDF, which is how I could use chi-squared scores to get my p-value. So my lower value is going to be 8.12. That was my chi-squared that they told me about. I didn't even have to find it. They did it all for me. And I'm going to go to an upper value of 99. Some people even tell you to go to 999, but basically we're just going way far up towards infinity. Now, here's the trick. What is my degrees of freedom? So many people want to do sample size -1 or maybe sample size -2. No for categorical data when we're working with chi-squared. So here's how we find the degrees of freedom. We have two variables. One is running experience. There's 3 categories. So we're going to take 3 categories -1. Then we're going to talk about the other variable, and that is, did you experience, again, whether or not you experienced an injury. That would be 2 categories. Yes, I experienced an injury, or no, I didn't. And we're going to take that 2 -1. So we're going to take categories -1 for the first variable, categories -1 for the second variable. We're going to multiply those together. So 3 -1 is 2, 2 -1 is 1, 2 times 1 is 2. So I have 2 degrees of freedom for this problem. So I'm going to go back to my calculator. I'm going to type in that 2 degrees of freedom. Hit enter here, and I get a p-value of 0.017. So is it greater than 0.25? No. Is it in between 10 and 25%? No. Is it in between 5 and 10%? No. It's in between 1% and 5% because my p-value, again, I showed in the calculator there, was 0.017. So it's greater than 1%, but less than 5%. Pretty simple as long as you know what to do. But the trick to this question is really being able to calculate those degrees of freedom. So many kids mess that up. All right, in this final problem here, an athletic trainer wanted to investigate the relationship between an athlete's resting heart rate and the heart rate after exercise. From a sample of 12 athletes, the athletic trainer recorded each athlete's resting heart rate in beats per minute and heart rate in beats per minute. after 5 minutes of moderate exercise. The results of the regression analysis are shown in the table below. So again, another one of these computer output tables that has everything I need in it. And of course, they want me to construct a 95% confidence interval for the slope. All right, the first thing I got to do is find the slope. Remember, in this first column, alphabetical order, A, then B, and B is your slope. So my slope is 1.786. So I can immediately get rid of A. They use the y-intercept instead of slope. All right, then we're going to go up and we're going to go down by our margin of error, which is going to be our critical T star times our standard error. All right, let's talk about getting that T star first. So I'm going to go to second vars and use invert T to get my T star. A 95% confidence interval puts 0.025 at the bottom. I've already mentioned that in that video. 95% in the middle, 5% left out. Symmetry puts 2.5 at the bottom, 2.5 at the top, and that's exactly the area it's asking for, is the area at the bottom. Now, what about degrees of freedom? Well, when you're working with slope, it's your sample size minus 2, so 12 athletes minus 2 is 10 degrees of freedom, and we get that same T-star we actually saw in the earlier problem, 2.228. That immediately gets rid of B and C because they had a wrong T-star. So 2.228. Now, what about my standard error? Again, no formula needed. Again, there is a formula for standard error, but all you got to do is look right next to slope, and bingo, there it is, 0.453. Nothing needs to be done to that number. That is the standard error for your sample slopes. So choice E is going to be my correct answer here, and I could walk away knowing I got this problem correct. So very small amount of questions in this video, but on the AP exam, there's not going to be a ton of multiple choice questions that cover chi-squared and inference for slope. Usually we're looking at a very small amount, maybe one of each, maybe even two of one or something like that. But these couple questions really do incorporate the different types of problems that you could possibly see in the exam that come out of dealing with chi-squared and inference for slope. So hopefully pretty easy, and hopefully there'll be some simple multiple choice questions that you should get correct.